Hello. So I've received some feedback in recent days from various people that I hadn't chiding me for not having posted anything on my YouTube channel for a while. And so today I am going to oblige you, and this video is going to be about how to complete the guided notes part 2 on drawing Lewis structures. So let me get to a PowerPoint presentation. So let me just go back here for a second. It starts with talking about drawing structures of polyatomic ions. Then it goes on to talking about various exceptions to the octet rule, and then how to draw the Lewis structures of compounds that are exceptions to the octet rule. So let's jump into the slides. Okay, the first subject is drawing polyatomic ions. Polyatomic ions, as you'll recall, or maybe do or don't recall, but I've said before, polyatomic ions are essentially like molecules that possess charges. And so those polyatomic ions contain covalent bonds, and they can be drawn as Lewis structures. The only difference between drawing the Lewis structure of a neutral molecule and drawing the Lewis structure of a polyatomic ion is in counting the valence electrons. And also, there will be another thing you do at the end, which is simply to draw brackets around the structure and assign a charge to it. But when it comes to counting the valence electrons in a polyatomic ion, we're going to make some adjustments depending on whether it's positively charged or negatively charged and what the magnitude of that charge is. Just like any ion, a polyatomic ion is charged because it either has more electrons than protons or fewer electrons than protons. So if it has a positive charge, you can essentially think of it just like as a monatomic ion. It has had electrons taken away. So when you do your count of valence electrons, you are going to subtract one electron for every positive charge of a polyatomic cation, and you're going to add one electron for every negative charge of a polyatomic anion. And the two examples that are on your sheet are ammonium and carbonate. So let's take a look at ammonium first. We're going to count the electrons similarly to what we would do for a neutral compound. There's one nitrogen. It has 5 valence electrons. There are 4 hydrogens. They each have 1 valence electron. That adds up to 9, but now there's a plus charge, so we are going to subtract 1, and that gives us a total number of valence electrons of 8. So 5 plus 4, but subtract 1 gives us 8. Well, we're going to do what we do with other Lewis structures when we're drawing ammonium. We're going to put the first element in the middle, and we're going to surround it with bonds to the other 4 elements. So there's atoms. So the first element in the formula is nitrogen, so we're going to put nitrogen in the middle, and then there are 4 hydrogens, so we are arranging them around the nitrogen, and we're drawing single bonds to each one. Now the next thing to do is to count up how many electrons we've used. We've made 4 bonds. Each bond contains 2 electrons, and so we've used 8 electrons. And so we've used up all of our electrons. We check to see if the octet rule is satisfied for everyone. Remember, hydrogen can only ever have 2 electrons in its valence shell. It can never make more than 1 bond. So those 4 hydrogen atoms are happy. The nitrogen is making 4 single bonds, so it has a complete octet. So we're done, except that, as I mentioned before, to be done, we actually are going to take and set a pair of brackets around the ion and put a plus charge to the side. And that's how we indicate that rather than being a neutral molecule, it's a polyatomic ion. Now let's look at the other example that's on your sheet, which is carbonate. Carbonate is CO3 2-. So if we count up the electrons again, there's 1 carbon that brings 4 valence electrons to the table. There are 3 oxygens, each of which brings 6 valence electrons to the table. That's a total of 22, but now we're going to add 2 more for the 2 negative charges on the ion to bring us to a total of 24. Okay, we're going to lay that out as I was describing with the ammonium. We're going to put the carbon in the middle. We are going to put 3 oxygens around it, and we are going to draw a bond to each. Now I notice just as I'm doing this and putting these slides up here, I kind of drew those oxygens in a kind of trigonal fashion, but it's perfectly fine to have 1 to the north, 1 to the west, and 1 to the east, or any sort of Cartesian way you want to draw it. I drew it in this sort of trigonal fashion, but you don't have to draw it like that. Okay, well, so now I'm going to count up how many electrons I've used. I have used 6 electrons to make my 3 bonds, which means that I have 18 more electrons to go. If I place them around my outer atoms, my surrounding atoms, I wind up using up the remaining 18 to put 6 electrons in pairs around each oxygen. Now, if I check that, I will see that that each oxygen, so I've used up all 24 electrons. Each oxygen has 8 electrons in its valence shell. However, the carbon atom only has 6 electrons in its valence shell because it's making 3 single bonds and there are no lone pairs on it. So we have talked in previous videos about, and also just if you've spoken to me off to the side, about what to do in this situation. You're simply going to pick one oxygen atom. It doesn't matter which one. I'm going to use the north facing one, and you're going to take away a lone pair and turn that into a double bond. So that's what I've done here. And now you can see that all of the oxygens have 8 electrons in their valence shell. 2, 4, 6 plus the bond makes 8. 2, 4, 6 plus the bond makes 8. 2, 4, and then 6, 8 for the double bond, and then the carbon has 2, 4, 6, 8 in its valence shell. So I'm done, except that once again I want to put brackets around my polyatomic ion and assign it a charge of 2-. Okay, let's move on to what's on the back of the sheet. And what's on the back of the sheet is a discussion of exceptions to the octet rule. We've talked about the fact that every atom, other than hydrogen, hydrogen cannot have more than 2 electrons in its valence shell because it's in period 1. But every other atom typically wants to have 8 electrons in its valence shell. But sometimes we will encounter molecules that have a central atom that does not have 8 electrons in its valence shell. And we're going to talk about the different possibilities of what might occur. One would be, and so there are 3 types of ions or molecules that don't follow the octet rule. One is when you have an ion or a molecule that simply, when you have correctly counted up all the valence electrons, there's an odd number of electrons. And we'll see in a moment that with an odd number of electrons, it's impossible for everyone to have 8, because in order for everyone to have 8, you must have an even number of electrons. Another one would be ions or molecules in which the central atom has less than an octet. So I'm going to actually, I want to change these slides just a little bit. I made these slides pretty quickly today. Ions or molecules in which the central atom has less than an octet. Ions or molecules in which the central atom okay, let's try going back to that. Okay. Ions are molecules with an odd number of electrons. Ions are molecules in which the central atom has fewer, oh boy, I'm not going to go back and fix that, but really, I'm kind of a grammar nut, should say fewer than 8 electrons in its valence shell. And ions or molecules in which the central atom has more than 8 valence electrons in its valence shell. And we call that an expanded octet. So let's take a look at examples of all three of those possibilities. First would be an odd number of electrons, and the most commonly given example of this is nitrogen monoxide. So nitrogen monoxide has 1 nitrogen, 1 oxygen. When you add that up, you get 11. So once again, it is impossible to draw a Lewis structure of nitrogen monoxide in which both atoms have 8 electrons in their valence shell. You have to draw it so that either one of the other or the other only has 7. And there are 2 reasonable options for this, and they're both shown here. In this instance, oxygen has 8 electrons in its valence shell, 2, 4, 6, 8. Nitrogen has 7, 2, 3, 5, 7. Or you could reverse it, and you could put you could move one of these electrons over here, and so now it's the nitrogen that has 8 and the oxygen that has 7. As it turns out, the one on the left is the preferred one, but for reasons that we don't go into in this class. But that's an example of a compound that has an odd number of valence electrons. You can also have an example, instances in which the central atom has fewer than 8 electrons in its valence shell. Now, if we go back here, right, to carbonate, we got to a point in drawing the Lewis structure for carbonate where we said, oh, look, we've used all our electrons, but carbon only has 6 electrons in its valence shell, so we're going to fix that by making a double bond. There are 2 elements that I want to bring to your attention that we don't do that for. And those 2 elements are boron. When boron is the central atom, it's only going to have 6 electrons in its valence shell. And if beryllium is the central atom, it's going to have only 4 electrons in its valence shell. Even if it's possible to give it a full octet, just like we saw so in carbonate, it was possible to give the carbon a full octet, so we did what we needed to do. We turned a lone pair into a double bond. With boron and beryllium, we're not going to do that, even if we could. And that's for reasons that is kind of beyond the scope of this class. But let's just take a look at the example of boron trifluoride. Boron trifluoride has 1 boron, that's 3 electrons, 3 fluorines, each with 7 each. That adds up to 24. We're going to lay out the structure. We're going to put the dots around the fluorines. We're going to have used up our 24, but we're going to resist the temptation with boron to take a non-bonding pair and turn it into a double bond, like you see over here. And once again, for reasons that are beyond the scope of Chem Honors at St. David's School, this turns out to be the one in which boron only has 6 electrons in its valence shell. Turns out to be the dominant Lewis structure, the best Lewis structure. So that's your answer for BF3. Finally, there are elements, there are molecules in which the central atom has more than 8 electrons in its valence shell. So for example, there is a well-known and well-characterized compound, phosphorus pentachloride. Okay, well, if I set this out with phosphorus in the middle and 5 fluorines around it, it's impossible for phosphorus to not have at least 10 electrons in its valence shell because it's bonded to 5 atoms. So there are certain central atoms that can expand their valence shell. And they are elements that are in period 3 or below. So in other words, things that are in period 3, period 4, period 5. We're really not going to go further down than period 5. What would be some typical elements that we would see as central atoms having expanded octets? That would be phosphorus, like we've got here, sulfur and chlorine, which are in the same period as phosphorus, selenium and bromine, which are in period 4, iodine and xenon, which are in period 5. We've talked about the fact that noble gases never bond to anything else, but there are exceptions to almost everything in chemistry, and xenon is an exception. Xenon is a noble gas that will form bonds, and we'll talk about that a little bit more in person. So again, if you take PCl5 and you count up the electrons, you're going to get 5 for phosphorus, 35 from 5 chlorines is a total of 40. I take my phosphorus, I lay out my 5 fluorines around it. At that point, I've used 10 electrons, so I got 30 left. And I find that if I put 6 more around each fluorine, I have now used up all 40 electrons. All of the fluorines have 8 electrons in their valence shells, and the phosphorus has an expanded octet of 10. I think this is the last slide for you guys. Yeah, these slides are for AP Chem. So let me go back and just say this is the assignment that you have that'll be due the next class period. It is Lewis Structures worksheet number 2, and you should have been given a copy of this in class. I'm asking you to do A through E. So it's got 2 sides. You do not need to do the group F, but I'm asking you to do group A through E before the next class period. When it says simple molecules, these are all molecules that can be where everything is a single bond and everyone has a full octet. Just really, really simple, easy to do. Polyatomic ions follow the rules that we were just describing for drawing, for adding. In this case, you're going to be adding electrons to the count each time because these are all negative. These are all polyatomic anions. Multiple bonds. I'm going to give you just a little bit of guidance on multiple bonds. SO2 is easy. It's sulfur in the middle, separately bonded to 2 oxygens. Obviously, carbon monoxide, there's only one possibility, carbon bonded to oxygen. In the case of C2H2, which is called acetylene, the 2 carbons are bonded to each other, and then each carbon is bonded to a hydrogen atom. And for this molecule, which is called formaldehyde, carbon is the central atom. It is bonded to oxygen and hydrogen and the other hydrogen. None of those other things are bonded to each other. They're all just bonded to carbon. So carbon's in the middle. It's got an oxygen going off in one direction, a hydrogen going off in another direction, and a hydrogen going off in a third direction. Each of these will require at least one higher order bond. In a couple cases, actually, you're going to wind up drawing triple bonds. We go to the back. Here are examples of incomplete octets. BCl3, which is an analog of BF3, which we just saw in the slides, and beryllium difluoride, which, as we said in the slides, beryllium compounds only have 4 electrons in their valence shells. And then these are all examples of expanded octets. We've already seen PCl5. You're going to see a few more. One thing I didn't mention in the slides that'll be useful to you in doing group E is that in some cases, you will find that once you have drawn all your bonds and you have given every surrounding atom a complete octet, you will actually have more electrons left. And when you run into that situation, you put those electrons in pairs on the central atom. You're going to see this occur for BRF5. You're going to see this occur for XEF4, and you're going to see this occur for CLF3. In each of these 3 cases, what you're going to find is you're going to count up your electrons, you're going to lay out your structure, you're going to complete the octets of all the surrounding atoms. And then for these last 3, what you're going to discover is that you have extra electrons left over, and they go on the central atom in pairs. And by the way, it just occurs to me as I'm sitting here, that is also going to wind up being the case for SO2. Okay, that's the video. I hope you enjoy the worksheet.